Thanks for tuning in to this talk about lithospheric-scale MT over the Yilgarn Craton. This is collaborative work between myself, Mike Dentith at UWA, and Klaus and others at the Geological Survey of Western Australia. So why the Yilgarn Craton? The Yilgarn Craton is fascinating for a lot of reasons. It's an Archean craton, so it's interesting to look at just in terms of its continental evolution. And particularly it has some really interesting geochemical and isotopic patterns, like these older isotopic model ages in the western part of the craton and younger isotopic model ages in the eastern part of the craton. It's heavily mineralised, and also that mineralisation seems to follow some of these broader architectural trends. So understanding how that mineralisation formed in the context of the tectonic evolution of the Yilgarn Craton is really interesting. And can also help us as we explore for mineralisation in regions where we maybe don't have so much outcrop and so much knowledge of the geology. That's a really important reason why it was interesting to do MT in the Yilgarn Craton, because we know that there is all of this mineralisation there, and we're embarking on these really enormous programs like AusLAMP to collect MT and help us to explore in more greenfields regions. So understanding the conductivity structure beneath known mineralisation, like that in the Eastern Goldfields, and understanding what that MT tells us about the composition, especially of the lithospheric mantle there, and how that feeds into the mineral systems processes, is going to be really helpful for us to capitalise on that AusLAMP data in regions that are more greenfields. So this is sort of our motivation for doing this work, and these boxes show the survey location crossing across this isotopic boundary, which in our region in the western part is the Yuanmi, and in the eastern part is the Eastern Goldfields Superterrane. And it also crosses from, in the Yuanmi, in this region, there's not much mineralisation, and then the Eastern Goldfields Superterrane is really heavily mineralised. This survey is just a long period MT survey, so focusing more on the lithospheric mantle, and it's being supplemented by a broadband MT survey, which will give us a lot more detail of what's going on in the crust and take this kind of from the lithospheric scale through to the camp and deposit scale. But for these long period MT results, these are 3 slices through the model. So firstly, at 20 kilometres in the mid-crust, there's actually not a lot of structure in this model, but we can see some stronger crustal conductors that are more concentrated in the east, in the Eastern Goldfields terrain. At 40 kilometres, the model's actually almost quite bland, but some of these crustal conductors still continue down to those depths and actually extend up to shallower depths as well. But things get more interesting once we get into the lithospheric mantle. So now at 100 kilometres depth, there's this long sort of north-south trending conductor in the western part of the model beneath the Yuanmi. And in the eastern part of the model, it's in general is less conductive. And this is a feature that extends throughout much of the lithospheric mantle and is really the most robust feature in this model. So we can look at a cross-section along this northern line, and this was chosen because we have the most dense stations along here. So on the left here is a cross-section through that 3D model that I just showed you, showing that lithospheric mantle conductor extends really from about 80 kilometres down to about 170 kilometres, where we start to lose resolution. And also shows that in the crust, those crustal conductors are concentrated in the Eastern Goldfields Superterrane in the eastern part of the model. These data are actually quite 2D, so I was also able to run a 2D inversion of this. This allows us to test some features and just obtain a bit some finer resolution. But really, it's just confirmed most of those features in the 3D model. So we still see this mantle conductor in the western part of the model, and it's showing a lot more detail in some of those crustal conductors in the eastern part of the model. So importantly, we can interpret these MT models in terms of the composition of the lithospheric mantle. And for this, I'm using some software called MATE that was published by Sinan Ozaydin, my PhD student, and I earlier this year. And this enables us to take those conductivity structures from MT and turn them into feasible composition and temperature structures. So here we're looking at the Eastern Goldfields. So the dashed line in the resistivity profile here is the resistivity depth profile through the Eastern Goldfields region. I'm particularly focused in the depth range of 100 to 150 kilometres because that's where the model is best resolved. So with this software, we can input a geotherm and an expected composition. So here I just have a very standard lithospheric mantle composition, olivine, pyroxenes, these nominally anhydrous minerals that we would expect to be in quite normal Archean lithospheric mantle. And with that, we can just add a little bit of hydrogen into those nominally anhydrous minerals, which increases their conductivity. And this can show us that just with that, this is enough to explain the conductivity of the Eastern Goldfields lithospheric mantle. There's no need for any additional conductive phases. In contrast, if we look at the Yuanmi, so now we're in the western part of the survey where we see that mantle conductor, do the same analysis, just having hydrogen in the nominally anhydrous minerals is not enough to explain the conductivity structure in the Yuanmi. So here I've put in an additional conductive phase, some phlogopite in this case. So the blue curve here is just including phlogopite in with the olivine and pyroxenes. And then in the red curve, I've also added some hydrogen into those nominally anhydrous minerals to really fit the data. So importantly, so the Yuanmi requires an additional conductive phase to explain the conductivity structure. So what can we take from this? So firstly, in terms of thinking about the metasomatism, neither region is totally dry and depleted and dehydrated as many people might expect from an Archean craton. And this is something we see time and time again from looking at Archean cratons with MT, that very often they contain more hydrogen and more metasomatic minerals than we might expect. But here we also see that the Yuanmi lithospheric mantle contains more metasomatic minerals than the Eastern Goldfields lithospheric mantle. And this might be a surprise because the Eastern Goldfields is more mineralised. And in most of the mineral systems models in general for these giant ore deposits, and certainly for those within the Eastern Goldfields, the models really show us that the lithospheric mantle has to have been metasomatized before as kind of a necessary prerequisite before those mineral deposits can be formed. So it might be surprising that the Yuanmi that is less mineralised seems to contain more metasomatic minerals in the lithospheric mantle than the Eastern Goldfields. But actually, I think maybe that makes a lot of sense because the MT is giving us a present day snapshot of the composition of the lithospheric mantle. And for that mineralisation to have come to the surface and formed those ore deposits within the Eastern Goldfields, there has to have been this low degree melting and a lot of mafic magnetism that has occurred to bring that mantle material up to the surface and form those deposits. And in that process, it's likely to have destroyed a lot of those metasomatic minerals within the mantle. They've been brought to the surface. So I think maybe it actually makes a lot of sense that we're seeing a slightly more resistive lithospheric mantle beneath the mineralisation within the Eastern Goldfields. And perhaps it also makes sense that we're seeing instead crustal conductors that may have formed as part of that process of bringing all that material up to the surface. And this may help us in terms of building exploration models that we're not necessarily just looking for a conductor in the mantle, but we're looking to understand the processes that are going to have formed that mineralisation and how they're going to relate to the compositions and conductivities that we can see in the MT. Thank you.